Hey guys, let's give folks just a minute to show up. We've got about 10 people here now. We're going to start at about 9:03 or so, give people a chance to log on, and then we'll just start slamming through this. And that'll give me just a minute to adjust the focus on here. Okay, if you've already logged in, go ahead over to the chat box. Just go ahead and let's make sure that the chat's up and running. Everybody can go ahead and say hi just so I know you're here too. Okay, so it looks like that is good to go. I'm going to go ahead and swap over, get a review started. Okay, you probably hear my cat there in the background. He should quiet down pretty soon. Okay, we're going to work our way through about 9 topics. I posted a copy of this for you guys to work through also. First topic is going to be, and let me see if I can adjust the lighting a little bit in here. It's a little better. We're going to cover the idea of ionic versus molecular. So if we're going to be naming something, we've got to be able to pick out first if it's an ionic compound or a molecular compound. We have formulas, and we also have names that we're going to have to give chemicals. And it all boils down first to ionic or molecular and which one that we're dealing with. So if we look at something that's ionic, it's going to either contain a metal and or a polyatomic ion. Now, we had a list of 10 polyatomic ions that we had to memorize. So to be able to ID these, we've really got to be able to spot polyatomic ions. The other half to this is a molecular compound. Molecular compounds are just going to contain nonmetals. So when it comes to identifying our first example here, it says, is the formula Li2S molecular or ionic? So let's look at the periodic table. So just roughing it out here. S is up here. Here's your stair step. Anything that's on the upper right-hand side of the stair step, these are all your nonmetals. But if you look over here on the left side, that's where you're going to find lithium, because we have 2 elements here, both lithium and sulfur. Lithium is on the left side of the stair step. Anything on the left side of the stair step, a metal. Because this formula contains a metal, we can answer this question. Li2S is going to be an ionic because ionic compounds contain metals or polyatomic ions. We're going to spot one of the two. Okay. So let's take a look at the counterpart for this. The counterpart for this is going to be something like NH3. Let me pull this up for you. Okay. NH3 has 2 elements in it, and one of them is a little bit tricky. If you look at the periodic table, We've got an N over here. We've got an H over here. And we've got that stair step that we just talked about. Just going to rough it out. Dividing the nonmetals on the upper right from the metals that are on the left. Our job is, again, to decide molecular or ionic. Now, there's a curveball. Even though hydrogen's over here, hydrogen is still considered a nonmetal. It's the only oddball on the left side of the table that actually is a nonmetal. So, quick question. You guys can type it out in chat. If I have NH3 that I'm trying to identify, and it contains all nonmetals, what am I looking at? Something that's molecular or something that's ionic? Go ahead and vote in chat and let me know. Okay, Nick, Jesse, Steven, all going in the right direction. So ultimately, choosing molecular, recognizing that this is all nonmetals, this is all going to play into what kind of formulas we're going to write, what kind of names we're going to give. The first starting point is molecular or ionic, so we've got to have a firm grasp on that one. Okay, let's keep rolling, because we've got till 10 o'clock to cover as much exam material as we can. Okay, next topic. We've got to decide, if I have an ionic compound, what's the charge on my ions? So let's sketch out the periodic table again. This time we'll be a little more careful. Okay. We had ionic compounds, and ionic compounds contained ions. If it was a polyatomic ion, it was an ion that contained poly or many atoms, something like NO3 with a minus charge. Polyatomic ions are ions, collections of atoms that have a charge. We had to memorize their charge. But what's nice, now Bindu, let me share my screen with you. Hold on, if you guys are having issues with resolution, and I'm going to swap over so you can see this. Okay, if you're having issues with resolution, you can go to your YouTube screen, go down to settings, and you can change the quality up to 720, or you can change it down to 144. If I change it to 144, I see my screen's getting all blurry. You can force it, or try to force it, to go up to 720p. That should clear up the picture some. Okay, so here we go. If we're trying to figure out something like N, and if N forms an ion, what's the charge on the ion? Let me stop sharing there. Hold on. That way you can see what I'm doing. If I'm trying to figure out the charge on an N ion, it's not something we have to memorize a list of. It's something we can figure out based on where it is in the table. If I go to the table, I can draw in my groups, and we're going to label these by group number and by charge. So this is group 1 on the periodic table, and group 1 has a +1 charge. Go ahead and type out in chat, what would it make sense for group 2 in the periodic table to have a charge of? All right, good. So group 1 is +1, group 2 is going to have a +2 charge. Now we're going to skip everything that's in the center, because when we get to the transition metals, we get elements like manganese that have a number of possible different charge states. So I'm going to give you guys only the ones that we can bank off of. That way, if I say calcium. Calcium's in the second group. We know it's a +2. We don't have all these questions on what's its actual charge state. So let's head over to the other side of the periodic table. Group 18. Group 18 is going to have a 0 charge. Group 17, a -1. Group 16, -2. Group 15, -3. And this is just going from the right side of the table over 0, -1, -2, -3. And then there are two elements that I wanted you to know: aluminum and zinc. Just because they're commonly come across, aluminum, when it forms an ion, is 3+, and zinc, when it forms an ion, is going to be 2+. So recapping, +1 and +2 for groups 1 and 2. Going from the right side of the table, it goes from 0 and starts going more negative, -1, -2, -3. Aluminum is +3, and zinc is +2. What we just covered are called monoatomic ions, meaning if I have a single mono atom of aluminum and it forms an ion, meaning it's charged, then that aluminum will have a +3 charge. This question is saying when an oxygen atom forms an ion, what's the typical charge it will have? Well, oxygen is not in group 18 or group 17. Oxygen is in group 16. And anything in group 16, if we read down, has a -2 charge. So it says when an oxygen atom forms an ion, what's its typical charge? Based on where it is in the table, we can see an oxygen is going to have a -2 charge. Or we would represent this by saying oxygen with a 2-, or you could write this also as -2. Okay, just for practice, if instead of an oxygen atom, let's say that I gave you a fluorine atom, I said it was an ion, what's the typical charge that would be written up here for a fluorine if it formed an ion, the fluoride ion? What would be our number that we should write in here? Just go ahead and type her out in chat. Good. Okay, so I'm getting a couple of -1s, and that's what you would be looking at. Fluoride is in group 17, so that's going to be a -1 charge. We'd pop in a -1 charge for this F. Okay, one last thing before we move on. If you notice, I've got positive ions over here. I've got negative ions over here. So we can start to draw in kind of a trend. Positive ions, just to refresh, were cations. Cations are positive, and your metals tend to form these cations. You could think, I positively hate cats. Now you know I don't, because you heard a cat meow in the background. Technically my cat by marriage, but still we can go by I positively hate cats. If we jump over to the other side, we've got a negative charge. So I tend to see negative charges on the right, positive charges on the left with respect to the stair step. If cations are positive, then anions are my negative ions. So just keep that in the back of your mind for later. Cat's positive, an's negative. Remember, you guys can stop me at any point if you have a question and we can back up. Okay, we're going to use what we just covered to start thinking about finding charges on what we don't know based on what we do know. Okay, so the question is, what is the charge on the manganese in the formula MnO2 when, and we also are wondering if Mn is an anion or if it's a cation. So let's blow this up a little bit so we can work on it. I've got MnO2. Okay, between the Mn and the O2, go ahead and type out in chat, which one do we know the most about? Do I know the most about the Mn or the oxygen? Good. So Stephen and Jesse, Joshua, Tanya, everybody's pointing to oxygen. Okay. If we drew out our table, oxygen's all the way on the right about here. I've got group 18, 17, 16. So this was 0 charge, -1 charge, -2 charge. So every oxygen carries a -2 charge. So let's start thinking about that. If each oxygen is a -2 charge, and I've got 2 of them, then these are going to multiply. 2 times -2 apiece is going to give me a total negative charge of -4. The way an ionic compound works, we've got to divvy it up. This is supposed to be my positive side. This is supposed to be my negative side. And my total negative charge has to balance out with my total positive charge. So having 2 oxygen atoms at -2 apiece giving me that -4 total charge, I've got to have a +4 on this manganese to balance it out. So question was, what is the charge on the manganese? It's got to be +4 so it can balance out that total -4 charge on the other side. Now type out in chat the answer to this second piece. If the manganese has a +4 charge, am I looking at an anion or a cation? Which flavor? Good. Okay. I'm going to buy Jesse's answer there for cation. Okay, because when we looked over ions, if I have anything that's to the left of the stair step, it tended to be positive over here, tended to be negative on the other side. Positively hate cats, cation. Okay, also, if you have a shortcut, this manganese is a metal, and we're talking all about charges. We're talking all about ions. So if this is an ionic formula, they always follow the same pattern, and that's cation first, anion second. So really, we could answer the second half of this question without having to do any of the math. The manganese has to be a cation just because it comes first in the formula. Okay, let's try the next one. I'm going to set it up, introduce it, and then I want you guys to type out the answer in chat. So it says, what is the charge on the cadmium in the formula cadmium oxide? So I have CdO. We're wondering what the charge is on the cadmium. Now we know we have 1 cadmium and 1 oxygen, and based on what we did in the last problem, oxygen, just because of where it is in the periodic table, is going to have a -2 charge. So take a look at this, figure out what the charge should be on that cadmium, and type it out in chat when you're ready. Okay, Stephen, let's see, Nilk, Tanya, it looks like you guys are all going in the right direction here. Okay, first off, this is going to be a multiple choice exam. So let's say your choices were A, B, C, and D, and your choices were -1, -2, +1, +2. Just based on where this answer shows up in the name, it's going to be positive. So even if you're not sure, I know it's got to be positive because it comes first. I can cross out half the possible answers. So now I've got to choose between +1 and +2. So coming over here, I've got 1 oxygen at -2, gives me a total -2 charge. So my positive has to balance that out. So the cadmium has to be a +2 charge overall. Now Jessie took it a step further. She said this is a cation, and it has to be a cation because cations always come first, anions always come second in ionic formulas. Good. Okay. Does anybody have any questions on these before we keep going? Okay, if not, then I'm going to keep rolling, and we'll start going over your polyatomics. Okay. I had a really good question on discussion board 2, which was meant to prep for this review session. The question was, you gave us this list of 10 polyatomic ions. You know, I hate memorization, which personally, I hate memorization also, but there's no shortcut. Post a copy of this on the door of your fridge, post it on beside your bed, post it in the bathroom on the mirror, whatever you've got to do, flashcard it up. There's 10 of these. You want to know the formula, you want to know the name for the formula, and you want to know the charge. So if I asked you, for example, the name for the formula, NO3 minus 1, you'd want to be able to snap right out of memory, oh, that's nitrate. And the only way we're going to get that is by memorizing this list of 10. So I'll give you a hint. There is going to be a problem where you have to identify one of your 10 polyatomic ions. So there's a really big payoff just for memorizing these 10, because they also come back in future classes. Okay, but going back to the list here, just an issue of memorization. The formula PO43 minus, you would look through your list here. PO43 minus, phosphate. And it's a cation or an anion. Well, phosphate has a -3 charge on it because it's a -3 charge. That makes it an anion. Okay, so we get phosphate as the name of PO43 minus and anion as the charge. Okay, I think more of what you guys came for were formulas and naming and stoichiometry and limiting reactants, and we're getting to those now. So we're really going to name one of each. We've got to name the formula CO and name the formula CaSO4. It all goes back to being able to name these as ionic or molecular to start with. So on the periodic table, you'll see me draw this a fair bit tonight. C and O are both on the upper right. That makes carbon and oxygen both nonmetals. If they're nonmetals and the whole formula is made of nonmetals, that means this is going to be molecular. And for molecular compounds, we've got to use prefixes. And just like the polyatomics had to be memorized for ionics, your prefixes had to be memorized for molecular naming. So that's things like mono being 1, di being 2, tri being 3, and so on. And we had a couple extra rules to deal with also. Now, if we try to name CO, we've got to indicate on this molecular naming how many there are of each. There's 1 C, 1 O, and we use prefixes to do that. The catch is that we never ever use mono to start a name. Prefixes go everywhere else. If there were 2 of the first one, we would still use di. The only prefix you ever omit is mono on the first part of the name. So I'm not going to name this monocarbon. I'm just going to name this carbon. Just the name straight off the periodic table. And you will have a periodic table that has all the names on it. O is oxygen, but we have to do a little bit extra with that. We left the mono off the first part just because we have to, but the second part needs a mono. So this is going to be carbon mono oxygen. So something's still wrong. We're going to have to change the ending, not to monooxygen, but to monoxide. So we get carbon monoxide. You'll notice I also did something else in here. We had a double vowel. Double O's, you've got to eliminate. Just one. It's not going to be carbon monoxide. It's going to be carbon monoxide. So just to recap, took the name straight off the periodic table for the carbon, took the second half of the name, oxygen, changed the ending to IDE, and then we had to add the prefix mono, eliminate that double vowel, so we get carbon monoxide. Okay. Now there is a subtle but important difference here. When I'm naming CO, I had molecular compound, I had to use prefixes. If I was naming something like this, and I've been known to throw this on an exam before, CaCl2 is not molecular. You might have choices for naming this of calcium chloride or calcium dichloride. And it's really tempting to want to throw that di in there, but di is a prefix. Prefixes go with molecular compounds. We wouldn't have to use any prefixes for a compound like CaCl2 because this is ionic. This contains a metal that's on the left side of the table. If it contains a metal in the formula, we're looking at ionic. No prefixes like di. We would just call this calcium chloride. We'll go through the naming rules for ionic compounds, but just keep that in mind as a really common mistake. If it's molecular, use prefixes. If it's ionic, no prefixes ever. Okay, let's head down to name CaSO4. So naming the ionic formulas a little less complicated. We don't have to worry about prefixes. We do have to know our polyatomic ions though. We take the name straight off the table, Ca, calcium. Second part of the name, we can't get off the periodic table. It was on our list of 10 polyatomic ions. So SO4 is going to be sulfate. So nothing more intense than that. We don't have to do anything funky with the 4 because an SO4 is just a sulfate. So calcium straight off the table, sulfate from memory. I want you guys to try something. Let's try MgI2. Let's try naming MgI2. I'll give you some choices. Choice 1, monomagnesium iodide. Choice 2, magnesium iodide. Or C, we'll have magnesium diiodide. Which choice do you think we should go with? Should I name MgI2 monomagnesium iodide, answer A, magnesium iodide, answer B, or answer C, magnesium diiodide? Okay, I'm getting kind of a mix of answers here. So let's break this one down. Just like calcium, magnesium is on the left side of the table. So it's a metal. So if it has a metal in it, that means that this is ionic. And if it's ionic, no prefixes. So we can immediately cross out answer A because it contains mono. Good. Brooke, Tanya, Bindu, anybody who's going for answer B, you're going in the right direction. Okay. No prefixes, so we can also cross out answer C because this is ionic. But let's see why answer B is right. we had magnesium straight off the table, and then iodine becomes iodide. So most ionic compounds, you're going to drop the ending, and you're going to go with an IDE ending. So just keep that in mind. If you end in IDE, you're barking up the right tree. The only time you end in something funky like an ate, an ite, an us, or an eum is when you have a polyatomic ion. Okay, it's going to feel like we're moving fast, but that way I can make sure to cover a few more topics, something for everybody, and you can always go back and watch this at the end. Do make sure that either participating or definitely stop me if you have a question. Okay, so I'm going to change this up a little bit just so we can make the example a little cleaner. The problem says calculate a molar mass. Now, like I said a few minutes ago, I'm going to give you a copy of the periodic table. So let's say we want to calculate the molar mass of, let's do CO2. Now, if I have to calculate a molar mass, we're going to have to go to the periodic table. I'm going to write out what of the periodic table we need. Okay, so if I was looking at the table, because I only have carbon and oxygen that's in my formula, I'm going to want to look at their masses, their average atomic masses that are at the bottom of each block. I'm not interested in the 6 or the 8, the atomic numbers. I'm interested in how much they weigh. So I'm going to take the number of each atom and type of each atom. So I've got 1C, and that carbon weighs 12. I've got 2 O's, because the little number subscripts apply to what they're directly next to, and those weigh 16 apiece. So 1 times 12 plus 2 times 16, which is 32. You add it all up, 12 plus 32 gives me a total of 44. And the units, when we're doing a molar mass, are going to be the number of grams that show up in a mole of the substance. That's why it's the molar mass. Mass in grams for every 1 mole. Okay, based on what we just did, I want you guys to try to find the molar mass of hydrogen peroxide. Hydrogen peroxide is H2O2. I'll give you a little excerpt here of the periodic table. You've got H and you've got O. I want you guys to add up a molar mass based on what's given here. So when you have an answer, pop it into the chat. I want to add up a total molar mass for H2O2. Okay, good typo fix, Jesse. Okay, so 34. Okay, so just to quickly work it out, we've got 2 H's, and they're 1 apiece. We've got to add to that 2 O's, and those are 16 apiece. So we get 2 times 1, which is 2, plus 2 times 16, which is 32. Add it all up, we get a total of 34 grams per mole. Okay, seemed like everybody was good to go on that one, which is good, because that's a precursor to some of the later work, which includes conversions. Okay. So first of these conversion problems, I know this was a popular topic when I looked at the discussion board. How many moles of H are present in 1 mole of ammonium acetate? Okay, so we're not as worried about in-depth conversions right now. Right now, we're just worried about chemical formulas. We want to know about total H. So we've got 1 mole of this compound, so I'm going to put a 1 out front. I'm going to write out the chemical formula. Now, if it had said I have 2 moles, I would have put a 2 out front, or 3, a 3 out front. So the coefficient that we pop out front is going to multiply all the way through, because big numbers out front distribute all the way through the formula, whereas these small numeric subscripts only apply to what they're directly next to. So if I'm looking for just H's, because it says how many moles of H are present, I'm going to take this 1, I'm going to multiply it where I see H's. So 1 times 4 would give me 4 moles of H from here. And then I've also got to do 1 times the H's over here. So that's 1 times 3, 3 more moles of H. That gives me a total, 4 plus 3, of 7 moles of H. So you can't just take one spot. The 1 times 4, you've got to look for all the H's throughout the formula. So final answer, 7 moles of H. Okay, using that same logic, it says how many moles of O are present in 1 mole of calcium nitrate? So I'm going to put a 1 out front, a Ca, NO3, 2, and I want you guys to type out in chat how many moles of oxygen you think are present in this 1 mole of calcium nitrate. So remember that 1 distributes all the way through, and you have to factor in those little numeric subscripts. So go ahead and type out in chat how many moles of O are present. Stephen, I think you were taking it another step and looking at grams. We're just shooting for moles here. Okay, so I'm going to buy into the 6. Okay, just let's ignore the 1 for a minute. I'm getting a number of 6's, which is the right answer. Okay, if I didn't have this 1 out here, and I asked you how many O's there were, we'd focus on this 2 and say, well, the 2 applies to everything that it's right next to, and it's right next to a set of parentheses. Just like if I had 2 plus x, and I had a squared on the outside, the exponent that's on the outside applies to everything that's inside the parentheses. So when I go back to calcium nitrate, the 2 applies to both the N and the O, but we don't care about the N. We're just asked about the O. So I've got 2 times 3, or 6, oxygens that are hanging out there. When you take that 1 into account, it multiplies through also. 1 times 6 leaves it at 6 moles of oxygen that are in that formula. Okay, let's hit some balancing. There were a couple of these problems that we work slightly differently than the others, but at the heart of it, we're trying to balance 1 atom at a time, or 1 polyatomic at a time when we're taking shortcuts. Let's try this first one out. Okay, this first one, what kind of reaction do I have here? Is it single replacement, double replacement, combustion, combination, decomposition? What do you guys vote? What kind of reaction is present? And we'll go over reaction types also now. So just go ahead and type that out in chat. You had a choice of combination, combustion, single replacement, double replacement, or decomposition. Okay, good. Combustion. All right, so we're going to go through each one of these. Before we go and balance them, we're just going to identify the type of reaction. You're going to have some type of fuel, and this is usually a hydrocarbon, plus O2. You've got your gas here. That's going to go to form CO2 and H2O, so in a complete combustion. Okay, good. People are chiming in with combustion. We're going to have fuel plus oxygen goes to CO2 and H2O. So I can change this piece. This fuel could be C6H6, it could be C3H8 if it was propane. So this is going to change, but you're always going to see these remaining pieces. Combustion requires oxygen. If you light a candle, so we get a little candle going, and then you put a lid on the candle. Candle goes out because you've removed the oxygen. Where you had a combustion reaction, that oxygen has to be present. Okay, still moving. We're going to hold off on this guy here until we balance it, and then I think it'll be a little more clear what type of reaction it's going to be. Let's focus on this one. We've got an element by itself and an element by itself. So when we start, we have a loner element. When we end, we have a loner element. And let's track what happens to it. When we start, the copper is with the sulfate. When we end, the copper's off by itself. When we start, the silver's by itself. But when we finish, the silver's paired up. So a single element comes in and replaces a copper. So this is a single replacement. It's kind of like cutting it at a dance where you have two people dancing, one person off by themselves, and this person over here decides to come in and say, hey, can I dance with this person? And he's like, oh, sure you can. So then you now have a new pair and an element gets kicked off by itself. Okay, so let's keep moving. Last one here. We've got two substances forming one substance. You can think of this by what they call it at McDonald's. When you are at McDonald's and you buy a burger and a fries and a drink and they package it all together, it's called a combo because you're taking multiple items, packaging them together. So here I've got C6H6 reacting with H2, forming one. This is a combination or combo reaction. Okay, so let's back this up. We're going to run through and balance all of these. Okay, never start with a 17. Start with something easy. Easiest number I can think of, 1. And combustion reactions, we're going to balance in a special order, CHO or CHO. That's the only of the reactions that we really have a special order for because it makes things a little easier. 1 times 5. Whatever you put out front as a coefficient multiplies through. So 1 times 5 gives me 5 C's. So over here, the goal is to get the same number of carbons on the other side. So if I put a 5 in this side, 5 times 1, if you don't see a little numeric subscript, it's just 1. 5 times 1 gives me 5 C's. So out of my CHO, my C is done. Next up is my H's. So I'm going to bounce back to the other side. 1 times 12 gives me 12 H's. So now I need 12 H's on this side. If I put a 6 here, 6 times 2 gives me my 12 H's. Okay, so this is kind of a red alert moment when you're trying to balance this. You've got to balance the oxygens last, and they're the toughest because they show up in 1, 2, 3 different places. However many O's are on this side have to match my O's that are on this side. 5 times 2 gives me 10 O's on this side. 6 plus 1 gives me another 6 O's on this side. Put that together, 10 O's and 6 O's. I've got a total on the right side of the reaction of 16 O's. What am I going to put in this blank to give me my 16 O's on the left? Go ahead and type it out in chat. What should go in the blank in front of O2? Good. So I'm getting some 8s. When you put that 8 there, 8 times 2 gives me 16 O's on the left also. So remember the goal, balance it, order CHO. Don't try to look at everything globally and try to balance everything at once. Okay. Let's move on to the next example here. We don't have a CHO to go by because this isn't a combustion reaction, but I can just pick something that's not balanced to start with and try to make it work. So I'm going to pick AGs. If I start just looking at the AGs, start with an easy number. If I put 1 here, that gives me 1 times 2, 2 AGs on the right. If I go over on the left, 2 times 1 gives me 2 AGs on the left. So I'm just picking one element to start with, kind of at random, and trying to make this work. All right, when I put this 1 over here, this gave me 1 times sulfate. Now let's make life a little easier. I don't want to balance the S and the O's individually, but this is off your list of 10 polyatomic ions. It starts as an SO4, and it ends as an SO4. It stays intact. So why not try to balance this as a group? I've got 1 SO4 total on the right side. What am I going to put here in this block to balance that out? Do I need a 2 here, a 1 here, a 3 here? What do you guys vote should go in this blank to balance out my SO4s? Good. Yeah, 1's going to go on the blank, because 1 times a single SO4 is going to give me that 1 SO4 on the left. Last thing is my coppers. 1 times 2 gives me 2 coppers. So I can put a 2 here. That gives me 2 coppers also. So if you guys notice, it's kind of like a tennis match. We're bouncing back and forth where the arrow is the net. So never staying too much on one side. We put a number, see how it affects it, move to the other side, see how it affects it, and just bounce back and forth. Now, we wouldn't want to try with 1. Oh, I see what you're saying. Let's try with 1 on the copper. Yeah, bingo. Okay. So next guy up. N2O4 goes to NO2. We held off on identifying this reaction just because it's not clear until you balance it. But the trick is we only have to pick one element to balance because the other one's going to take care of itself. We've got 2 N's here. If I put a 1, that gives me 2 N's. So over here, I can put a 2. And that gives me 2 N's. My N's are balanced. 1 times 4 gives me 4 O's. 2 times 2 gives me 4 O's. So we're done. This was a really quick reaction to balance, but it's a little harder to see what we've got going on. If we looked at this in terms of a picture, I've got N2O4, and what I'm going to do is I'm going to take that molecule and split it. When I get over here, I'm going to have this when I get over to the product side. I had 1 piece. When I get over to the products, I have 2 pieces. Is this a combination, a decomposition, a combustion? I'll give you a choice of the 3. Just in chat, what do you think? Is this a combination, a decomposition, or a combustion? Good. Okay. When you think decomposition, I always think to show like Walking Dead or zombies where you have parts falling off and pieces falling off. Really, it's a breaking apart. So if I start with N2O4, I start with one more complex molecule. I'm breaking up into multiple pieces, multiple components. So it's one making many. Okay, so a decomposition reaction is correct. Okay, let's go down for our last one. This looks like it might be a combustion reaction, but it isn't. It starts out with that hydrocarbon, but we don't have the O2, the CO2, or the H2O. Really, this is our combination reaction that we just looked at. So let's start with an easy number, 1. I'm going to start with C's. 1 times 6 gives me 6 C's. If I put a 1 over here, because remember we're bouncing to either side of the net, 1 times 6 gives me 6 C's. Now it's time for the H's. 1 times 12 gives me 12 H's. And over here, what do you guys vote that I put in this blank to make that work, to balance out my H's? Be careful on this one, it's a little bit tricky. What should I put in that blank to balance out my H's? Okay, good. So I'm seeing a lot of 3s, and that's heading in the right direction. When we have C6H6 on the left, I've already got 6 H's. I need a total of 12 on this side, so I only need 6 more. If I put a 3 in this blank, 3 times 2 gives me that last 6 H's, so total. Okay, I'm back. Hopefully you guys can hear me. I'm on wireless audio right now, so I've got to periodically cut it back on. Okay. Just give me a type out in chat once you guys can hear me, but should be up and running again. Okay, conversions. Something really, really good to memorize is this chart. Where we have mass, moles, molecules, and atoms. Okay. The reason this is so good to memorize is because it tells you how many parentheses you need in your conversion. It also tells you what conversion factor you're going to need to move from mass to moles. Need the molar mass. So if you get a tattoo for this exam, this is it. Molar mass you get from the periodic table. Okay, if I'm going to go moles to molecules, I need Avogadro's number, and that number is 6.022 times 10 to the 23rd, and the units on it are molecules per mole. And then last, if I want to go from molecules to atoms, I'm going to use the chemical formula. So if I'm using H2O, that's the formula I'd use. If I'm using carbon dioxide, I would use CO2. So our first problem says take 11 grams of CO2 to moles of CO2. So I'm starting in grams. Grams is mass. I'm going to moles. That's right next door. So picture yourself standing on top of this little brick, Mario style. If Super Mario needs to jump across, he's just jumping across one block. The number of blocks that I jump are the number of parentheses that I set up when I convert. So I'm going to start with the number that they give me. They only give me 1. I'm going to set up 1 parentheses because I'm only jumping 1 block from mass to moles, because that's where the problem's taking me. Okay. To do this, I need the molar mass off the periodic table. CO2 is something we added up earlier, but let's add it up again. We've got carbon, we've got oxygen. Carbon is 12 apiece, oxygen is 16. I've got 1 carbon at 12 based on the formula. I'm going to add to that 2 oxygens because it's CO2, and these are 16 apiece. 12 plus 32 gives me 44 grams per mole. This is our molar mass that we're going to need for this conversion. So my question now, where should the 44 go? Give me a vote. Should the 44 go in the top or the bottom? Okay, so I got to go vote for it going on the bottom. I'm going to buy that. Let's fill in things that we want to cancel. Opposite sides cancel. Grams started out on the top, so grams are going to go on the bottom because I don't want to end in grams. I want to end in moles. I'm going to put moles in the top because then they'll stick around. I'm going to put the 44 with the grams. Whenever you're converting, not stoichiometry, but whenever you're converting, 1 always goes with the per mole. So we've got 11, multiply by what's in the top, divide by what's in the bottom. So 11 times 1 divided by 44 works out to 0.25 moles, and this was moles of CO2. So it's a super key skill because in stoichiometry we have to work in moles. So being able to get to moles, really useful. Okay, the second one was pretty commonly requested on the discussion boards, and this is pretty much the hardest problem that I could give you on an exam for conversions. So let's take a look at the details on this one. It wants me to go from grams, which is mass, over to atoms. So I've got to start here and end here. So let's count. I'm going 1 block over, 2 blocks over, 3 blocks over. So I can set this up as a triple conversion. I only have 1 number to start with, so I'm going to start 9 grams. 1 conversion factor, 2 conversion factors, 3 conversion factors. Because I jumped 3 spots, I need 3 conversion factors. Going back to our chart, first one's going to be molar mass, second one's going to be Avogadro's number, third one is going to be chemical formula. So let's label this. So I need molar mass, I need the Avogadro's number, and I also need the chemical formula. Or in this case, since we're dealing with H2O, the chemical formula is H2O. Okay, just to speed this up so we can get to the stoichiometry, H's are 1 apiece, the oxygen weighs 16, that means that my molar mass is 18 grams per mole. Avogadro's number is always the same, 6.022 times 10 to the 23rd, and that's molecules per mole. Okay, so what I'd like to do is set everything up unit-wise, and then we can start filling in numbers. Molar mass is in units of grams per mole. I want grams to go away, so I'll put them on the bottom. Avogadro's numbers in terms of molecules per mole. I've already canceled grams, but now I need to put my molecules per mole in. I'll put the moles in the bottom, that way they'll cancel. I'll put the molecules in the top. And then our last one, our chemical formula, is going to be atoms the unit on this is atoms per molecule. So when we go to put this in here, I want to cancel out the molecules because I want my final answer in atoms. So I'm going to put molecule on the bottom. I'm going to put atoms. And really, this is atoms of H in the top. So let's start filling in numbers. My molar mass was 18 grams for every 1 mole. My Avogadro's number for every 1 mole, I had 6.022 times 10 to the 23rd molecules. For my chemical formula, we're looking for atoms of hydrogen. So let's focus on H2O. For every 1 H2O molecule, 1 entire molecule, I've got 2 H atoms. So that's what goes in here. For every 1 molecule, I have 2 atoms of hydrogen. Okay, just double checking everything. Molecules canceled with molecules, moles canceled with moles, grams canceled with grams. We set everything up so that opposite sides would cancel, leaving us with atoms of hydrogen for our final answer. And then we multiply everything across the top, divide everything across the bottom. So 9 divided by 18 times Avogadro's number times 2. Let's see, that should give us an answer of 6.022 times 10 to the 23rd. Now, let me see if I can get this working. I'd like to show you guys how to type that out. We'll see if this calculator will actually pick up, and it looks like it is on the screen. Good. Okay. So I've got 9 divided by 18, and let's see, do I have a caret sign on this? You know what? I actually don't have the right calculator. This is my financial calculator. So we're going to switch over. And I'm going to show you guys on a Google calculator. Okay. Let's pull up Google Calculator. I've got 9 divided by 18. Oops. Go to Google really quick. 9 divided by 18 times Avogadro's number, 6.022, times 10 to the power 23. And I want to also multiply that by 2. And it gives us the answer, 6.022 times 10 to the 23rd. I wanted to bring something up. If you guys got that on an answer, are you guys still with me? Chantel froze. Now it does show me that I'm still broadcasting, and I've got about 4 bars. You can't use Google on the exam. The reason I didn't use Google is because I have a financial calculator. You can use a regular calculator or a graphing calculator, but no Google. I'm just showing you how to type it out. You'd actually type that out the same way. Oh, nice. Okay, Stephen. I do have students that want to use it, though, and sadly you can't. It is a pretty fantastic calculator. Okay. So just wrapping this up, 6.022 times 10 to the 23rd, and that answer would be in terms of atoms of H. Okay. So the document that I sent out earlier, check your email. I want to make sure you guys are getting all your resources. I do have this review or a similar review that's fully worked out, that has videos, sample problems worked out, so you can go back and look over a couple of these. Okay, I realize it's 10 o'clock, but I also realize that a number of you wanted to go over stoichiometry problems. So I'm going to stick around and finish up these last two practice problems. Okay, I'm going to leave the ionic formulas to the review though, because I am going to need to call it in a few minutes, and we have covered a lot in the last hour. Okay, how many moles of H2 are needed to react, let me move this to where you can see it, with 12 moles of N2 based on the reaction below? Okay, so this is stoichiometry. This is predictions. This is how much do I need of one thing to make something else. So there are two things that you need. I need moles for one. Number two, I need to be balanced. So if the reaction isn't balanced, then balance it. If I don't give you moles, get moles. So these are two things that you need to have in the back of your head as key things that you have to have handy when you start a stoichiometry problem. So starting this off, I've got one N here and two of them here. So if I want to balance this, this gives me two N's. That'll give me two N's. 2 times 3 gives me 6 H's. 3 times 2 gives me 6 H's. So now my reaction balanced out. Look in the problem, they give me 12 moles of N2. So I've got moles to start with. So once you have moles and once you have a balanced reaction, you're ready to jump into any stoichiometry problem. You just have to identify want and have. So I have 12 moles of N2. That's what the problem gives me. I want moles of H2. And really, when you do stoichiometry, you really only need to know, Jen, you're right. You can watch this later after the review's done. We're going to be running a few minutes late going over the sample problem though. Okay, you only need two coefficients. You're going to need what you have and what you want. I'm starting with N2. I'm trying to go to H2. So I'm going to need this, and I'm going to need this. So this sets up just like a conversion. I'm going to start with my 12 moles of N2. And then I need to cancel my moles of N2. And I need to end with what I want, moles of H2. And then to get what goes in here number-wise, you go to the coefficients. A 3 goes with the H2 and the balanced coefficients. So a 3 is going to go with the H2 down here. A 1 goes with the N2. 1 goes with the N2. So 12 times 3 is going to, divided by 1 is going to give me 36 moles of H2 because my moles of N2 cancel out, leaving with moles of H2. So just to recap, had to have moles, check. Problem gave me moles. Had to balance it, went through and balanced it. That's why balancing is a key skill. If balancing is off, the rest of the problem is going to be off. You write down the one number that they give you in the problem, the ratio of what we have and what we want comes from the coefficients, multiply across the top, divide across the bottom, got our final answer. Okay, suggestion, if these are rough, you can always go back, replay this, try it yourself, and then see it worked out fully for you. Okay, so I'm going to go ahead and fill this in because we're dealing with the same reaction. It has the same coefficients. It says how many moles of NH3 will be produced when 4 moles of N2 is reacted with 4 moles of H2. So we've got a curveball here. Let's label our haves and our wants. For my have, I've got 4 moles of, let's see, 4 moles of N2 and 4 moles of H2. And it says how many moles of NH3 will be produced. So my want is moles of NH3. So this is a little confusing because the first problem we did only gave us one value. This one gives me 2. So when you have 2 values, this is more like a Limiting reactant problem. Okay, so with a limiting reactant problem, you do it the exact same way. You're just going to do twice the work. So let's just look at a similar example here. If I had, let me flip this over so I'm not writing our problem. If I had 4 slices of bread, pardon my artwork, so 4 slices of bread, and I've only got 1 slice of cheese. How many grilled sandwiches could I make based on that? And this is for anybody in chat. 4 slices of bread, 1 slice of cheese. How many grilled cheese sandwiches could I make? Yeah, Jesse, Chantel, I could make 1. And that's because to make a grilled cheese sandwich, I'm going to need a piece of bread on the bottom. I'm going to need some cheese on the inside, just 1 slice, and then I'm going to need a piece of bread on the top. So really, I've got enough bread to make 2 sandwiches. I've got enough cheese to make 1 sandwich. But when you look in reality, what can I actually make? I can only make 1 sandwich. And why? Because I'm going to run out of cheese. That means my cheese is limiting. I have extra bread. I have 2 extra slices of bread. So we could say that our bread is in excess. Really, this problem that we're working on is grilled cheese chemistry. It's the exact same math. You guys just solved a limiting reactant problem. It just didn't have a chemical formula in it. So I'm going to ignore the fact that the H2 is present and just look at that 4 moles of N2. Okay, and just like before, I'm going to try to get rid of the moles of N2 because I don't want those. What I want is moles of NH3. So I'm going to put moles of NH3 in the top. Moles of N2 cancel. 1 goes with the N2. 2 goes with the NH3. 4 times 2 over 1, 8 moles NH3. Okay, not done yet though, because we just looked at the N2. Now we've got to look at the H2. I've got 4 moles of H2 also. Same way, I want to get rid of the moles of H2. I'm going to put it on the bottom so it cancels, and I want to end with moles of NH3. 2 goes with the NH3. 3 goes with the H2. 4 times 2 divided by 3 is going to give us 8/3, or that works out to about 2.67 moles of NH3. So let's flip back. In our grilled cheese example, the bread said I could make 2 sandwiches. The cheese said I could only make 1 sandwich. Which one was right? The one that predicted less. So when we go over here, based on my N2, it said I could make 8 moles of NH3. Based on my H2, it said I could make 2.67 moles of NH3. So 2.67, about 2.7 moles of N3 or NH3 is the right answer. You go with the smaller of the 2 answers. So don't get fancy. Don't add or subtract them. Just go with the smaller answer. Okay. Whatever is used to predict the smaller answer is limiting. So in other words, the H2 runs out first because it predicts the smaller answer. The N2 was excess because it predicted the larger answer. Okay. Wrapping this up, this is our last topic here, and that's writing chemical formulas. Good news is it's a smooth move to the finish, or a smooth ride to the finish. First one has us writing the formula for the compound dinitrogen tetroxide. Okay, first off, type out in chat, if I have prefixes, what does that tell you about this? Is this ionic or molecular? Just because there's prefixes present, like di or tetra, am I dealing with an ionic compound or a molecular compound? Good. Okay. So only prefixes for molecular compounds. And di means 2. Tetra means 4. So we're going to have nitrogen being N. Oxide refers to oxygen with the "ide" ending. So I'm going to have N and O, 2 N's, because of the di's with the nitrogen, 4 O's because the tetra is with the oxide. So our formula is going to be N2O4. So as long as we know those prefixes, we can write the formula pretty quickly. Second one is a little more involved. Write the formula for the chemical compound strontium nitrate. Well, you're going to have a periodic table with names on it. So if you see strontium and you're not sure the element symbol, don't guess. The worst thing you can do here is guess, because if you look at potassium, the element symbol would make sense if it was P, but it's actually K. Strontium would make sense if it was something like ST, but it's actually SR. So take a minute, look at your periodic table during the exam, and make sure you're getting the right element symbol. So SR is strontium. Out of memory, has to be a memorized polyatomic ion. When you see 8s, ites, ems, anything other than ide, think polyatomic ion. So I've got SR paired with NO3, but we're still not done. This has a metal in it. If you looked at the periodic table, strontium shows up about there. So we're looking at something to the left of the periodic table. This is a metal. It also contains a polyatomic ion, so we're looking at an ionic compound. Ionic compounds don't use prefixes, they use charge to balance them out. Nitrate has a -1 charge. Strontium is in group 2, so it has a +2 charge in that second column. So we're going to take the +2 charge on strontium, we're going to cross and bring it down. We're going to take the 1 and bring it down. Just a little note here, you don't bring down the sign. These little subscripts tell you how many. So it wouldn't make sense if you brought down a -1, because then you would have -1 strontiums. Just bring down the size of the number, not the sign on the number. Okay, so when we're done here, we can't leave these charges up here. The charges just helped us figure out how many of each. So now we're done. The formula for strontium nitrate, we don't have to show the 1, that's just assumed, is SrNO3 2. So recapping, molecular compounds, prefixes told us how many of each. For ionic compounds, you've got to know the charges, cross them and bring them down, and you get your overall formula. Okay, so that was the last topic of the evening. We've gone about 25 minutes over. I'm going to have to call it for the night. Thank you guys for coming. If you have an exam later in the week, make sure to come by office hours. I do have office hours on Tuesday, Wednesday, and Thursday of this week. Wednesday, I'm in the STEM Center, so come see me. You guys can also send me email questions. Be as specific as you can when you send those. So everybody have a good night. Thank you for coming. And I'll keep an eye out if anybody has any questions.